According to Pew Research, about 52% of US adults recently just completely walked away from a product or service. Why? Because they were absolutely terrified of how much of their personal data was being collected. I mean, that's more than half the population. But here's a crazy thought. What if the exact same machine learning architectures that process all our data could actually be used as a mathematical shield to protect it? Welcome to today's Explainer. I am super excited to get into this because we're looking at a piece of neural network architecture that honestly feels like absolute magic. We're talking about autoencoders. We're going to see how these models compress data, how they can clear up fuzzy medical images, and how they might just be the key to keeping your biometric data safe. All right, so here's our game plan. We'll start with a really quick look at the unsupervised learning landscape, then map out the sort of hourglass shape of an autoencoder. After that, we'll upgrade it for images, break down the frankly clever math of transpose convolutions, and finally look at some real-world life-saving applications. Let's get into it. Starting off with Section 1, the unsupervised learning landscape, and how we actually find hidden structures in raw data. Okay, so before we actually build an autoencoder, we gotta understand why we even need one, right? In unsupervised learning, we are working with datasets that don't have any target variables, no labels. We are kind of flying blind. And our goals here can be anything from data compression and clustering to exploratory analysis and eventually generating completely new examples. Basically, we need a tool that can just look at raw data and inherently figure out its underlying structure. So this brings up an interesting showdown between a classic technique, principal component analysis, or PCA, and our main event today, autoencoders. Now you might be thinking, hey, if PCA is this super efficient matrix factorization method that finds maximum variance really fast, why even bother with a complex neural network? Well, here is the kicker. Autoencoders use non-linear activation functions. That is absolutely crucial because it means they can capture super complex, non-linear relationships in the data that PCA would just completely miss. We minimize the mean squared error during training, and then boom, those compressed representations can be fed straight into classic machine learning models like random forests or used for transfer learning. All right, let's jump to Section 2 and see what this actually looks like when we build it. We're stepping inside the autoencoder hourglass. To really get autoencoders, you have to understand the core, which we call the latent space or the bottleneck. This is basically the heavily compressed, embedded representation of your input data. By forcing our data through a literal physical bottleneck in the network's layers, we brutally restrict the flow of information. The network has literally no choice but to toss out the noise and keep only the absolute most essential structural info. It's a real sink-or-swim situation for the data. And visually, this forms an hourglass shape. It's a three-part journey. First up, the encoder acts like a funnel, compressing the input features down layer by layer. Second, we hit that bottleneck we just talked about, where data is at its most compressed. And finally, the decoder takes over. It grabs that ultra-compressed latent data and tries to blow it back up to match the original input. And honestly, that's the most mind-bending part of all of this. The target output of the network is simply the input itself. Moving on to Section 3. An hourglass made of standard, fully connected layers is totally fine for flat data. But what about images? For that, we need to upgrade to image convolutions. Let's actually watch this learning process happen. Here we have an autoencoder trying to reconstruct the famous MNIST dataset, the handwritten digits. Up top is the original image, and below is the network's attempt to reconstruct it from that tiny bottleneck. In these early training epochs, the output is basically just blurry, undefined smudges. The network is totally guessing. It hasn't learned the hidden rules of a 28 by 28 pixel image yet. But wait, look at what happens mid-training. As that mean squared error drops, the network adjusts its weights, and those smudges start turning into actual, distinct edges and shapes. You can clearly start to make out the loops of the 8s and the sharp angles of the 7s. It's kind of beautiful to watch. And then, in advanced training, wow, look at this. The reconstructed row is practically indistinguishable from the original. The network squashes a full image down into a tiny handful of numbers in the bottleneck, and then perfectly redraws those sharp digits from scratch. It is absolutely not just memorizing the pictures. It has genuinely learned the structural rules of handwriting. Okay, but how? How does the decoder flawlessly upscale that tiny bottleneck data back into a full-resolution image? That brings us to Section 4, expanding outputs with transposed convolutions. So, a regular convolution takes a larger area of pixels, shrinks it down to a single value, and slides across the image. That's how our encoder compresses things. But then we have the transposed convolution. This is the exact opposite. A single pixel from the input map is projected outwards to create a larger grid in the output. This neat mathematical sleight of hand is exactly what lets the decoder inflate that tiny latent space back up to the original image dimensions. Now, there are a few nuances to this. Obviously, it's great for increasing our output feature map size, but the terminology gets a little messy. You might hear it called an unconv or a fractionally strided convolution. You will also hear people call it a deconvolution, but mathematically, that is technically incorrect. Because true deconvolution is the exact inverse of a convolution, which this isn't. Also, a quick heads up, these can sometimes cause weird visual checkerboard artifacts in your generated images. Because of that, a lot of modern engineers actually prefer to just use a standard interpolation upsampling followed by a regular convolution. But to ground all this abstract math, if you're actually coding this in PyTorch, it's incredibly simple. You literally just call a single function converse transpose 2D. You hand it your input channels, output channels, set a kernel size of 3, no padding, a stride of 1, and you're good to go. And the math underneath it is surprisingly elegant. Let's break down the formula for the output size. It's the stride multiplied by the input size minus 1, plus the kernel size minus 2 times the padding. So say you have an input size of 4, a kernel of 3, a stride of 1, and 0 padding. Plug those in. 1 times the quantity 4 minus 1, that's 3. Add the kernel of 3, you get 6. Subtract the 0 padding, and boom, your 4x4 input matrix just seamlessly expanded into a 6x6 output matrix. Easy, right? Now that we've got a handle on the math and the architecture, let's head into Section 5 and check out the real-world power of all this: denoising and privacy. Autoencoders get seriously powerful when we throw in something called dropout layers. I like to call this the magic trick of denoising. During training, we deliberately mess up our input data. We literally add static or just drop out pixels entirely. But, and this is key, we still force the network to calculate its error against the clean original image. By doing this, the network has to learn highly robust, redundant features. It literally learns how to ignore the corruption and reconstruct the clean reality hidden underneath. And here is why this math actually matters in the real world. We can use models trained on noisy audio to actually strip out background interference and enhance human speech, which is an absolute game changer for hearing aids and telecommunications. Or think about medicine. A convolutional denoising autoencoder can take heavily corrupted, grainy medical x-rays and turn them into crystal clear diagnostic images. The network uses its latent space to understand what a human bone structure should look like, and it simply refuses to decode the static. It's literally saving lives. Which actually brings us full circle to that 52% of Americans we talked about at the start, the ones terrified of data collection. Enter the privacy shield. Researchers have built these semi-adversarial networks that use convolutional autoencoders to subtly modify images of your face. The autoencoder looks at your photo and adds these tiny mathematical perturbations. Now, these changes are completely invisible to the human eye, and they still let biometric systems, like the Face ID on your phone, recognize you perfectly. But they completely scramble unauthorized third-party AI classifiers that try to scrape your age or gender from your photos. The autoencoder acts as a mathematical filter, protecting your identity from predatory algorithms without breaking the tools you actually want to use. So I think the really big takeaway here is this: machine learning isn't just about extracting our data. It's also about transforming and protecting it. As autoencoders and semi-adversarial networks become even more advanced, how will the ability to mathematically compress, denoise, and subtly alter our personal data reshape the entire future of digital privacy? It is a fascinating frontier. Thank you so much for joining me on this explainer today. Keep learning, keep questioning, and I will catch you in the next one.